This is Kinesiology 200, Intro to Functional Anatomy. The chapter is actually Anatomy and Physiology. Keep in mind that this is a 1 year long, so 2-semester course that you'll be taking in your kinesiology pursuit. And if you're on to graduate school, you'll be taking 1 year of anatomy and physiology in your undergrad, another year of anatomy and physiology in your graduate, with an occasional course, maybe like neuroanatomy or a specialty course in that. And if you're looking at just kinesiology, you'll be taking an additional course called functional anatomy, which is in addition to your anatomy and physiology. And as we get into Module 3, exercise physiology, that's an application of the physiological system. So this is the starting point, and by no means are you expected to be an expert in anatomy and physiology. This is meant to be purely an introduction, just scratching the surface to kind of get a taste to what academic studying in this field may bring. So when we look at this particular focus of anatomy and physiology, even if you're just focused on human anatomy, when we looked at human anatomy with human movement, particularly with kinesiology, you're going to look at just some of the main systems. So getting into the digestive system or into the reproductive system, looking at the skin or the hair, the nails, these systems aren't as, not that they're not important, but they don't play a major role in movement. So when you look at where we'll focus at in the kinesiology is going to look mostly in the musculoskeletal system, neuromuscular system, and then these two support systems of getting blood and oxygen to there via the cardiovascular system and the respiratory system. Now this slide was in their introductory lecture, and I said this is a really great slide because it kind of provides a roadmap to what's happening with anatomical aspect. And if we look down here, this is where we have our movement, right? And this is where we look at kinesiology, the study of human movement. And the way that we interpret this pyramid here is that this is a chain of command, a hierarchy of control. This is reflective or encompassing of the human movement system. And this term articular system is looking at the joints, the skeletal system, but it's including all the connective tissues, so ligaments, joint capsule, cartilage. And the way this is read is that movement occurs here at the articular system. The articular system is 100% in control, controlled by the muscular system, and then the muscular system is 100% controlled by the nervous system. And so there's a flow of information where the signal starts here in the nerve. This blue explosion, comic book pow type thing, that represents conscious thought. So you have a thought, and this could be subconscious thought as well. It actually represents thought. And the nervous system then takes that desire, that need, that drive, whatever it is, and it codes it into electrical digital signal that is then sent down the line through the nerves to the muscular system. The muscles receive that signal. They do the only thing they know how to do, which is contract. They change their electrical signal into a mechanical force. That mechanical force is applied to the joint, and the joints then produce movement. So it's a very complex system, but simple in terms of this flow of command. And so like what we looked at we'll go back one slide here with this skeletal, muscular, neuromuscular components. You'll see here that this is the focus of kinesiology. When you look at functional anatomy, this is it. And then you have the cardiovascular system and the respiratory system that are supporting these metabolic outputs for this musculature. So the very first start in anatomy is being able to describe terms, and it starts with an anatomical reference point. And this reference point that you see depicted here in the picture with legs straight, arms straight, and palms facing forward, this is referred to as anatomical position. And so when you start to describe or start to understand or read about a three-dimensional space, being able to talk in the same coordinate or the same context is very important. So you start to get these relative comparisons, these terms. And the one thing I do want to mention, and you'll see the next slide a bunch of anatomical terms, one of the most difficult aspects that comes to studying anatomy and physiology is outside of the sheer volume of stuff that you are going to be exposed to. One of the hardest aspects is the terminology is new. So think about taking a foreign language class and a science class with a whole bunch of memorization all at once. And this is why anatomy and physiology, particularly anatomy, has one of the highest failing rates of any course sequences that exist within college. it's acceptable to have up to a 50%. So I think they shoot for like 41 to 46% DFW, which means D, failing or withdrawal weight. So you're getting almost 50% of the people that are dropping out or not doing well in these classes. And it's not science in terms of you're not calculating anything, you're not trying to figure out a vector or trying to figure out the molar mass or the molecular weight of a chemical. It's straight up memorization. Now, there's some application, and people kind of miss the boat by that, and we'll talk more about that later in the semester. But I think one of the biggest aspects is that it's a foreign language added to a anatomy class. So if you ever have a chance to take like a medical terminology class before you sit for an anatomy and physiology exam, I think we have in our health science core, HSC or HCS 112 here at Harper, it would be a great class to take just to get that initial exposure. Then when you actually sit for your anatomy class, the terminology isn't so foreign to you. So you see these 4 points here, 1, 2, 3, 4, and you'll see these relative comparisons for 1 is superior to 2, 2 is inferior to 1, and you can make other references like 3 is more lateral than 1 and medial. And so when you read through your textbook, you'll see some of these comparisons for how things are related to one another. Now, the reason why it says relative is that, let's say we look at the shoulder here, and we can say that the shoulder is indeed superior to the elbow. Or another way of looking at it is the elbow here is inferior below the shoulder. But when we look at the elbow compared to the wrist or the hand, the elbow is now superior to the elbow, whereas before it was inferior to the shoulder. So that's what relative means, is that it's always comparing something to something else. So you have to know both points in order to make that comparison. So the next slide kind of gets into the description of what's superior, inferior, lateral, medial, proximal. And for instance, anterior, meaning towards the front of the body, in normal conversation, we'd say the front of the body, or we'd say the back of the body. But in anatomical aspect, we talk about anterior or posterior. We'd refer to left or right, but we more look at medial versus lateral. So again, when you start to talk about certain anatomical structures or particular movements, not only are you adding having to think about what's going to happen visually and abstractly, but now you have to start coming up with the new anatomical terms, the titles that we use for this, so you can see how it can get very complex. Now, since we're dealing with 3 dimensions, so you're going from your textbook, right, 2 dimensions, and you're talking about the human body, which has depth and structure, more complexity to it than just the 2 dimensions. We have a coordinate system that we use to describe particularly movement of the human body. And so what happens here is this 3-dimensional coordinate system, these X, Y, and Z planes, have particular cardinal names. And so you have the transverse plane, the sagittal plane, and the frontal plane. And the frontal plane divides the body into front and back, or anterior and posterior halves. The transverse plane divides the body into superior and inferior, or top and bottom halves. And the sagittal plane, right down the center here, divides the body into left and right halves. And you can see that these 3 planes here make this 3-dimensional coordinate system. You're going from a square to a cube, or a circle from a sphere. And the reason why this is important is when we start looking at human movement, remember, all movement occurs at the articular system, and movements occur only at joints of the body where 2 bones come together. And those bones are depicted as like a hinge or an axis. And so when you look at this here, you see the wheel, and you see this wheel spinning. What this allows us to kind of start to visualize is that we have a fixed axis of rotation. So you see that axle is not really moving. It's not moving left or right, up and down. It's spinning, it's rotating in space, and the rest of the wheel is rotating about that. Now, no joint of the body does a full 360 degrees, but we do levels of like from 0 degrees to, let's say, 120 degrees, or 0 degrees to 50 degrees. And when we look here at like the knee joint here, say this is 180 degrees right there. And if we look at the leg going from straight curling, we'd say from here to there is about 90 degrees. That's 135, and that's about 160 degrees. So you're getting 160 degrees of knee flexion and then back to 0 degrees of extension. And so all human movement is based on this fixed point, this joint. The stability of that joint determines the type of movement. And when we start looking at like biomechanical analysis for exercise or sport, we do a lot of looking at how much range of motion we have, or what degrees are happening, or what mechanically is available there. In order to talk about this, we have special terms for those, and we have not only those 3 planes, sagittal, transverse, and horizontal, or frontal, but you have axes that run through there. So you have the transverse axis, anterior posterior axis, and longitudinal axis. Now again, for this class, it's meant to be an introduction. So these are going to be terms that you're going to see. I don't expect you to memorize any of these things. You will in your future classes, but for now it's meant to just be a general initial exposure to the complexity that's going to come along with just the terminology alone for anatomy. So let's start looking into the three systems. We're going to start here with the articular system. Remember, this consists of the skeleton and the connective tissues. We divide the skeleton into two separate systems. We have the axial skeleton, which is highlighted here in blue, and then you have the appendicular appendages, arms and legs, that's also depicted in blue on this other image here. There's about 80 bones in total for the axial skeleton and 126 for the appendicular. And the best way to kind of look at this is that when things come in pairs, that's probably the appendicular skeleton, and when it's single right in the middle here, it's the axial for axis. Now the ribs are the only thing that throws that statement off, but if you think of the ribs as a continuation of the thoracic spine, that kind of fits right along. The next image here kind of shows those two together, and again, here are all the bones, the major bones of the body, and not only do you need to know the bones themselves, but you'll need to know all these bumps and fossas and shallows and different odd-shaped spine of the scapula, because all these things serve as muscular attachments. And to best understand how the body moves, you need to know where those muscles are attaching to, how they're pulling, and how those bones are moving. Now there's four types of bones of the body. Most of the bones that you're familiar with are long bones, but you do have flat bones, you have irregular bones and short bones, and in the end, bone is bone. These long bones are load-bearing. The bones act as levers for the muscles to pull off of. And the one unique aspect here is that the long bones, because of the bone marrow here, that's where your red blood cells are produced. The other bones here, they don't have that level of blood production, but they do serve as a deposit for minerals and anchors and levers for muscles to pull off of. Here's your 5 functions of bones, which you can go through and read through. Most people look at it as a structure of the body, and it's true. But if I were to take all the bones, there's a cartoon that used to go around where if all the bones came out of the body, it'd be like a blob, or just a mass on the ground. And that's actually not true. The bones don't actually give structure. The bones are rigid levers for the muscles to pull off of. You are actually a bunch of fluid in cylinders, and it's like you're a big water balloon, or several water balloons that are put together. And your structure actually comes from fluid mechanics. So the bones really are transmission for the muscles that are producing, or that are pulling, and it's producing the movement there. So the other tissue besides the bones, you have the joints where the two bones are coming together, and then you have this connective tissue, ligaments, and then tendons, so ligament and tendons. And there's another thing that's not listed here, it's called fascia. And if you're somewhat up to date within the fitness industry or the rehab industry, fascia has become the superstar, if you will, or the hot topic in the manual therapy fields. All of it's made up of the same stuff. It's a high collagen, so ligament, tendon, and fascia are all made up of similar aspects, just varying in levels of density based on what they're doing. Ligaments connect bone to bone, tendons connect muscle to bone, and fascia connects everything else. And fascia is very vast, and that's why it was kind of overlooked in the body. It's like, it's all over the place, we don't need it. But they're finding that it actually has ability to communicate, it helps with structure, tension pulls, and there's just so much that we're learning about it. Thomas Myers has a really good book called Anatomy Trains if you want to look further into that aspect. When you get into functional anatomy or even structural anatomy, you'll look at the types of joints, their articulations, and you'll look at the different categorization, these immovable, slightly movable, freely movable, synarthroses and amphithroses. Again, more terminology thrown at you. Most of your analysis is going to be here with these freely movable, looking at like the hip, the knee, the elbow, and so forth. And then when you look at those movable joints, you'll find that they are even categorized further into 6 subcategories of like plane joints, saddle joints, and like here's your thumb, and this is the elbow and ball and socket joint. So again, just an introduction. As you read through or take some of the quiz questions, just force you to kind of work with the material a little bit, but again, just meant to be a basic introduction to anatomy. When we look at the actual movements that are occurring at the articulations with the joint movements, you have, again, a whole new list of terminology. So you have flexion, extension. This is movement that occurs in the sagittal plane. You have ab and abduction. This occurs in the frontal plane. and then you have rotation that's occurring in the transverse plane. And to make things more complicated, they have special terms for things that are happening at the wrist, like pronation and supination, inversion, eversion at the foot, dorsal or plantar flexion at the ankle, and elevation and depression at the scapula. So again, it just continues to get more complex, and there's no rhyme or reason to it. It's just a matter of becoming familiar with it by daily or normal usage of it in your normal terms. So in the sagittal plane, we introduce these terms flexion and extension. So flexion is the decrease between two bones, the angle. So when the bone's coming closer to another bone from anatomical position, that's considered flexion. And then repositioning back down when the distance getting greater, that's called extension. We have in the frontal plane, when things are moving away from the midline of the body, the center line, just like you would get abducted by aliens because you're taken away, you would be abducted, abduction. And then if I'm adding back towards midline, that's called adduction, ADD, adduction. To make things more complex, the description of the frontal plane in the appendicular skeleton is different than the spine moving at the axial skeleton. So when we talk about frontal plane movement from the spine, instead of talking about abduction and adduction, we use this term lateral flexion. So are you side bending to your left? That would be left lateral flexion. Or side bending to your right, that'd be right lateral flexion. In the transverse plane or the horizontal plane, when your segment or body segment is turning facing in towards midline, we call that internal rotation. And if it's turning out, external rotation. And then if we're talking about the axial skeleton, it's just are you turning to your right or turning to your left. There's this thing called Tri-Planar Motion, which is used in the reading, but it's called circumduction, and it's basically the ability to make a cone. You can do this with your finger, with your hip, and with your shoulder. So we move on from the articular system to the muscular system. And this is the largest organ system within the body. It can take up between 40 to 60% of your body mass. There are well over 600 muscles in the body, and it varies. Some people have certain muscles, some people don't. There's three main types: cardiac, smooth, and skeletal. So the cardiac muscle is found only in the heart. The smooth muscle is found in all the tubes of your body, so your blood vessels, your esophagus, digestive system. And then the largest amount of mass is the skeletal, which is called voluntary, but you really don't have that direct control over your muscles. You have control over joint output, but how your body recruits the muscles is up to the body. So you have different muscle arrangements. So you have these long cylindrical muscles, you have these bipennate, and so muscle shape determines muscle force. And again, I think it's more complex than this class offers. Just keep in mind that the shape of muscle can determine the force output or the role of the muscle. So when we look at muscle tissue, we are introduced to these terms, and we're starting to look at like mechanical properties, so we start to borrow some physics terminology. We have these terms extensibility, which is this kind of elastic aspect, this ability of the muscle to stretch and lengthen without damage. My next slide kind of talks about that a little bit more the plasticity versus elasticity. One of the things about muscle tissue, which is the second term here, which is excitability, this tissue has the ability to stimulate. Within milliseconds, it can go from rigid to like super flexible and loose within milliseconds. And it can go from like a slinky to a rod or a column within that short period of time. And then what that excitability does is it produces this contraction, this ability to generate tension, to produce force when needed. So back to the elasticity. If you can visualize in your head, or you can see the image here, a credit card, and there's a certain amount of play. So if I bend that credit card, you can see that it starts to flex. It went from straight to bent. And there's a certain amount of range of motion that I have that I can bend it and let go, and it'll go right back to its normal length. So that's the elastic range. But I get to a point where if I bend it too much and then I let go, I have physical deformation or change. And muscles, which are pretty unique, they can extend up to 150% their resting length. So there's quite a bit of pull or tension or length that can be generated out of that. When you do extend or go beyond that, you end up with some tissue damage, which like a pulled muscle or a torn tendon or a ligament or something. But it takes quite a bit to get to that end range. Believe it or not, most muscle pulls don't happen because they're overstretched. They happen because they contract too hard and the muscle rips itself apart. So when we look at muscle contractions, there's really only one type of contraction. The muscle's either contracting or it's not. So it's either getting a go signal from the nervous system and it's on, generating muscle tension, trying to pull the two bones closer together, or it's off. Now what can happen is the amount of tension being generated based on the external environment or the load, that can result in is the muscle contracting and it's shortening, so it's actually accelerating, so that would be a concentric contraction. Is it contracting but the load is winning, so it's like a tug of war and the muscle's not generating enough tension, so that'd be an eccentric contraction, or there'd be an isometric contraction where the load and the muscle tension is exactly the same. This kind of looks at, it's a great image, it kind of looks at the muscle structure and it looks at like how the muscle are this right here, this muscle fiber, is the actual cellular component of the muscle. And unlike most tissues of the body, cells need a microscope for you to be able to see. But these muscle fibers are about the length of, or about the size of a human hair. So, and they run from one end of the bone to the other, and they go the entire length. And when you break this down, really muscles are nothing more than like bundles of hairs that are bundled together. And if you ever looked at like a rope before, you would see how a rope is kind of twisted together. These aren't twisted, but they are bundled together into these different aspects, and that's kind of the structure that we look at with muscle. One of the unique things is when you gain muscle or lose muscle, you don't really gain any new muscle cells. What happens is these cells go from thin hairs to thick hairs, and the thicker the hairs get, the more muscle mass you have. But you're basically, the amount of cells that you, the amount of muscle fibers that you are not necessarily born with, but that you are matured with, so after puberty, are the same amount that you relatively die with. So there's really no added or subtraction of the muscles as time goes on. Within the muscles, you have contractile elements called myofibrils, these myofilaments, and the two main ones are actin and myosin. And you'll spend a lot of time learning about the sliding filament theory of how these muscles are, or how these proteins interact with each other to generate muscle tension. You have two different types of muscle fibers. You have fast twitch and slow twitch. Fast twitch are your high force but really exhaustible, quick to run out of gas. And your slow twitch, they can endure forever, but they don't have a lot of force. And there's really no such thing as converting one muscle fiber to the other. What happens is it's a spectrum of fibers that exist between fast twitch and slow twitch. And so you have all these intermediate fibers in between, and when you start to train, those tissues adapt. So you're not really getting conversion from like a red fiber to a blue fiber, but there's a whole bunch of purple fibers in between that the purple fibers will turn more slow twitch if you're doing more slow twitch activity, and then the purple fibers will turn more blue if you're doing more fast twitch activity. So when you look here at this graph here, you see marathon runners, and as you would expect, they would have a higher adaptation of the slow twitch fibers, and then sprinters, they would have a higher adaptation of their fast twitch fibers. But it's not because type 1 or fast twitch are converting to slow twitch, it's because those intermediate fibers, those kind of play in the middle, they start to tend one direction or the other. Now the muscle fibers need to be controlled by the nervous system, and that's where this motor unit comes from, this term motor unit. And it's the connection from the brain to the muscle fibers. It's like a light switch, not a dimmer switch, a light switch, and either muscle fibers are on or they're off. And then you're introduced to this concept of the size principle, which the smaller muscle fibers contract first and the larger muscle fibers contract later. So what this means is that if you're let's say looking to train your lower body, if you walk, that's a low intensity activity, the lower and smaller muscle fibers are going to be trained, but the larger muscle fibers will never be turned on. If you run, you'll recruit maybe slightly larger muscle fibers, and in order to recruit those smaller muscle fibers, or medium muscle fibers, you need to recruit those smaller muscle fibers. So jogging will make you better at jogging, and it will make you better at walking, whereas walking will only make you better at walking. Then if you sprint, in order to sprint, you'd have to recruit those small fibers, then those medium fibers, and then those bigger, larger fibers. So there's a trickle-down effect. When you do heavier weights or higher intensity activity, it makes you better in lower intensity ranges, but the opposite is not true. So if you train lower intensity, you're only going to get better at low intensity. It may not affect your higher intensity component. The job of the muscle is to produce tension, and that's it. That's all it can do. And so a muscle can only pull. it cannot push. So what is the unique thing here is that all muscles are paired in opposition in terms of this agonist-antagonist relationship. So you have one muscle that's producing tension, and you have another muscle at the same time that's relaxing. And then when you go to reposition, so let's say I go to touch my elbow, my shoulder, and then I go back down to straighten my arm, the agonist now becomes the antagonist, and the antagonist becomes the agonist. And that's what this looks like here. So here's your agonist. If I'm bringing my arm up to my shoulder, this would be the agonist, and this would be an antagonist. And that in this image here, it's showing the arm going down, and they're switching roles. And so you can kind of see this. Whoops, that was supposed to be there we go. So you can kind of see that again, that they switch roles based on position. So muscles cannot push, they can only pull. So when you have one muscle pulling, you have another muscle that's relaxing. In order to reposition, you have another muscle that's going in the opposite direction. And so muscles aren't only prime movers in terms of agonist and antagonist, they can also function as these other titles as like stabilizers, neutralizers, and synergists. So musculature has a supporting role, and there's quite a bit of complexity to it. So again, this is just looking at the musculoskeletal system, looking at the structure, some terminology and musculature. That's it for this particular part 1. There's part 2 that will get into the nervous system, cardiorespiratory, and the cardiovascular system.